Hello guys, this is the solid state relay that I made. This solid state relay is made on the basis of this Triac BTA41 600. It controls the loads up to 40 amps. It's not so neat and tidy, it's kind of messy, but anyway it works perfectly. There's so many soldering, and the components is not in beautiful order, but it works. Let's check to see how it works. So here it is, it's working. This is the microcontroller ESP32 VROOM 38 pin, and this is the relay module that I made, and this is the LED lamp. It works on AC 220 volts AC. So the AC current is coming from this wire, and through this Triac it's going to the LED. It's working. And the ESP32 microcontroller is programmed to blink this LED in every 1 second, and this LED shows the Triac is triggered and its pins are latched. When the signal inputs the relay module, this LED lights on, and this LED red LED only shows when this relay module is powered with 3.3 voltage, and this shows when the relay module is in operational mode. It connects these wires. It shows it's working perfectly. So this is the circuit of this solid state relay that I made using these components. Now I will explain this circuit in details, the components I used and the values of the components I used. I will explain. So this is the complete circuit of the solid state relay based on the BTA 41 600. This relay can handle up to 40 amps of current. They can flow through this Triac. So this is the trigger side. This is the optocoupler in the middle, MOC 3023, will trigger this Triac. So how it works? This is the 3.3 volts positive and negative, and this is the input signal which can be taken from ESP32 GPIO pin. You can see that the positive of the 3.3 volt goes to the pin 1 of the optocouplers through 150 ohm resistor, and the negative side of this circuit goes through this BC547 NPN transistor. I'm using this transistor in order to control this optocoupler with a little current. This trigger signal works with just only 1 milliamps. So if you apply 1 milliamps of current to this input pin, it will trigger the optocoupler, and the whole relay works perfectly. Through this input pin, I used the 2.2K ohm resistor to the base of the transistor, and with this I used 66k ohm resistor in order to pull down the base when there is no signal, because you know that this BC548 transistor is very sensitive. That's why you should use some pull down resistor in here. And this is the LED. It indicates if there is power on the terminals of the relay. It indicates, it lights on when you apply voltage to the main terminals of the relay. This is the second LED. It only turns on once the input signal is received, and the input signal is received, and this transistor closes the wires, closes the circuit, and lets the current flow to the optocoupler. So this LED turns on only when this optocoupler is in operational mode. Here I used the 1K resistor, but you can choose your own resistance depending on how much brightness you want from this LED. I don't want so much brightness, that's why I used 1K resistor. If you remember, it was the green LED blinking on the board, and this is the red LED in the middle on my board. It constantly turns on once the 3.3 voltage is applied. And this is the resistance of 150 ohm across between this positive and the pin 1 of the optocoupler. This is the this is the most important part of this circuit. You have to be careful when choosing this resistance, because the whole circuit, positive and negative, will come to this internal LED of this optocoupler, and this internal LED of this optocoupler requires certain amounts of current and voltage in order to be in operational mode. According to the data sheet of the MOC 3023, the internal LED's forward voltage is 1.2 volts, and the minimum current to trigger this LED is 5 milliamps, and the maximum current is 60 milliamps. I chose 15 milliamps to trigger this internal LED of this optocoupler. So this will work perfectly, and when you apply 15 milliamps of current to this optocoupler's pin 1 and pin 2, it perfectly latches the pin 6 and pin 4, which in turn triggers the Triac. So here is the formula, how I chose this resistance and this resistance to the base and the resistance to the optocoupler. Here is the formula. According to Ohm's law, we can calculate how much resistance we need. Here is the MOC 3023. Its forward voltage is 1.2 volts, and the V voltage reference is 3.3 volts that I'm applying from this positive and negative side. And the resistance that we should use in this place is calculated this way. So VRF minus voltage forward voltage, and divided by the current that is exactly needed to turn on this LED. It is 15 milliamps in my circuit. So 3.3 volts minus 1.2 volts divided by 15 milliamps. It approximately comes to this result of 140 ohm resistance, but I will use 150 ohm resistance as a standard resistance. It will work perfectly. There will be no faults with this resistance. So you have to be very careful to choose this resistance. This resistance only works with 3.3 volts. If you apply 5 volts of voltage to this circuit, you have to recalculate the resistance between the optocoupler and the power. This is very critical. So how I choose this base resistor in the circuit? Here is the calculation. So this is according to Ohm's law. The resistance is calculated this with this formula, you know, from previous calculations, and we have to take into account this resistance. With this resistor, 66K ohm resistor and 2.2K resistor, place a voltage divider in this place. So we have to calculate the output voltage of the base, the voltage that the base is consuming. We have to calculate this. So how to calculate the output voltage of this voltage divider? This is calculated with this formula. So voltage in multiplied by resistance 2 divided by the sum of resistance 1 and resistance 2. So we will get the voltage out. In my case, the supply voltage, you know that the input voltage is 3.3 volts. It's from the ESP32 GPIO pin, and pull down resistor here is the 66,000 ohm resistor, and the base resistor is 2200 ohm and plus 66,000 resistance ohm. The result will be 3.19 volts. So if you apply 3.3 volts from this input line, the base only receives 3.19 volts. So then we can calculate the base resistance from where I got this 2.2K ohm resistor. The input voltage for the base is 3.19 volts and minus 0.7 volts. Where I got this 0.7 volts? It is from data sheet of this NPN transistor. The base of this transistor is triggered with this voltage 0.7 volts. So it is the required voltage to trigger the base. So we will subtract this voltage from the input voltage and divide by the current. We will apply through this input signal. In my case, it is 1 milliamps or 1.001 amps. So it comes to 2,490 ohms of resistance. So how I got this 1 milliamp? According to the data sheet of this BC547 NPN transistor, if you use this transistor as a switch mode, it will amplify the input signal 20 times in the collector emitter terminals. So 20 times. I'll need 20 milliamps of current in order to trigger this optocoupler and this LED. Just 20 milliamps is just enough to trigger both of these components. So that's why I chose 1 milliamps of current will be drawn to this base of the NPN transistor. So the result is 2,490 ohms of resistance I have to put in this place, but as a standard resistance I used 2.2K ohm resistance. It doesn't matter. It doesn't make any difference with these resistors. You can use 2.2K ohm resistors. So with this 2.2K resistors and 66K pull down resistor, if he applies 3.3 volts of voltage with the current of 1 milliamps, this NPN transistor fully latches the emitter and collector, allowing current to flow to this optocoupler and turning on this LED. So this side of the circuit now works. I explained. So if you apply voltage and input signal to this input pin, it works. And the next part of this circuit is the AC load, AC 220 volts part. This is a circuit that with this circuit you can totally isolate the high power side with low power side. This optocoupler divides this high power side from this low power side. That's why it is very important to use these MOC optocouplers. So once the input signal comes to this circuit, it triggers the internal LED of this MOC, and in turn, if the internal LED lights on, it latches the pin 6 and pin 4, allowing to current flow through its pins and go into the Triac. This is the BTA41 Triac. In order for this Triac to close this A1 and A2 terminals, you have to apply some current to this gate. It is the gate terminal. So now you can see that the line comes will be connected to the A2 pin, and this optocoupler takes the current from this pin, from this A2 pin. Here is connected through 330 ohm resistance. This resistor is used to restrict the current flow to this optocoupler. It protects the optocoupler and limits the current, because the gate of this Triac only needs a few milliamps of current in order to trigger, in order to be triggered fully. So this resistance is used to pull down the gate when the circuit is off, and it prevents the false detection, false triggering of this Triac. So you can supply this high AC voltage, 220 volts. Typically it is neutral, and this is the line, because you have to put, it is better to put your load on the neutral side, because the line side may be quite dangerous to put on the load, because from this circuit you can see that if you apply line on this load, there's always a voltage on the load. That's why you have to put your load on the neutral side. And the line signal, line voltage comes through this line to the Triac, but Triac is cut those terminals, and the current will not flow through its pins unless the input signal is received. Once the input signal is received, it triggers the optocoupler, and the optocoupler in turn lets the current flow through its pin number 6 to pin number 4, and pin number 4 connected to the gate. The gate will receive some amount of current, and the A1 and A2 terminals of the Triac are latched, and the current flows through this Triac to the load. So this is how the SSR relay works. This is just a simple circuit you can make by yourself. If you have any questions or recommendations to improve this circuit, you can comment down on the below. There is cons and pros using this solid-state relay compared to the conventional relay. This is the relay I have made, the solid state relay, and this is the conventional mechanical relay. Both are used to control the high power AC loads, and it has its own advantages and disadvantages. For example, this solid state relay, the main disadvantages of this relay is that it dissipates some power. The voltage drop across this Triac A1 and A2 terminals is typically 0.9 volts, and if you, for example, control the 5 amps of load with this relay, it will dissipate more than 4 watts of power on the Triac. And compared to this mechanical relay, it dissipates some power. But this relay doesn't dissipate any power on its terminals, but its coil consumes some power. At least on the coil, it dissipates some power. It is usually 1 watts of energy. 1 watts of energy will be dissipated in its coil. So this is what I got here. If you have any questions or recommendations to improve this circuit, you can comment, as I said. Okay, bye-bye.